Hello everyone, I'm Austin Erickson. Today I'm going to be giving this talk about the effects of dark mode style user interfaces on virtual reality displays. So over the past 20 to 30 years, the majority of all our user interfaces on pretty much every digital device has been what's called light mode or positive contrast style interfaces. So on these we typically have a light colored background, typically white, and then on top of that we put our dark colored text, typically black. And it's been around since the first what you see is what you get text editors from the late 70s and early 80s. But lately we're seeing this trend back towards dark mode or negative contrast style interfaces, where we have this dark or black colored background and then this white or light colored text put on top of that. So over the past couple years, all of the major operating systems companies have released operating systems with these type of settings for our users. So Apple, Microsoft, and Google have all released OS updates that allow our users to pick dark mode. So what's interesting is that we're seeing this trend for everything except for AR and VR devices. And we're unique with our VR and AR HMDs because the display sits 1.5 inches or 2 inches away from our eyes, whereas for all other display mediums, you're sitting further away from it. So the benefits and drawbacks to these type of UI styles may be different for HMDs in general than they are for traditional flat panel displays. So just by having that display so close to your eyes, it brings up 3 different factors. One of which is that the screen door effect may be visible on the display, although this is getting better with increases in resolution and with the display technology itself. It's still a factor at the moment. The other 2 things are that the screen luminance may cause visual fatigue, and it may even change our user's pupil diameter. So we have these things that are more of a factor to HMDs than they are for other types of displays. So how do these factors impact our standards for UI design? We actually ran one study on this already, investigating optical see-through AR HMDs. For that we used the Microsoft HoloLens, and they have this other unique problem that since it is an additive light display, they can't render black text, just black at all. It just shows up as transparent. So when we ran a study comparing dark mode and light mode interfaces, we saw that dark mode both improved our users' visual acuity significantly, and it significantly reduced the amount of visual fatigue compared to light mode interfaces. So for this, we wanted to measure these same things on VR HMDs to see if we still had similar benefits there. So I mentioned earlier there were 3 factors we were considering, one of which is the screen door effect. So as you can see at the top here, if we use a dark mode interface, the screen door is kind of masked by that dark background, but then it has the drawback of appearing more prominently over the text that we're trying to read. And then the opposite happens if we use light mode. It's more prominent across the entire interface in general, but then it's less apparent on the text itself. We also have these factors of visual fatigue and pupil diameter. So with the dark mode style interface, you're typically introducing less light to the user's eyes, which will result in less visual fatigue and a more dilated pupil. Whereas if you have that light mode interface, you have more light reaching the eye, which typically results in more visual fatigue, a constricted pupil, and may have this interesting effect called the pinhole effect if the pupil size is reduced enough. That pinhole effect can cause an increase in acuity, as well as some other interesting effects here. So in some prior work by Jones et al., they investigated perimeter lighting or peripheral lighting, where they had a ring of LEDs around the inside of a VR head-mounted display. And they found that when these LEDs were turned on, that their users were actually better at estimating distances between objects. So they had improved distance estimation with this light turned on, a really easy thing to do. Again, those lights constrict our users' pupils, and it's also a known effect that this can cause an increase in visual acuity. So a very simple thing to try if we're looking to squeeze the most acuity for our users. We designed a study based on these three factors. So we have a 2x2x2 full factorial within subjects design, ended up with 18 participants. Our three independent variables were the color mode, which could be either dark mode or light mode. Then we have our virtual lighting, which as this study is taking place in virtual reality, we have a virtual environment that houses our user interface. It's either very well lit in a bright virtual environment, or it is a dimly lit virtual environment. Our third variable is perimeter lighting. So instead of introducing a ring of LEDs like Jones et al. Did in their work, we decided to illuminate the outermost pixels on the display. So the pixels on the top, bottom, left, and right are turned to white for so many rows in, just to add more light on the display with the attempt to constrict our users' pupils a bit. We did have three dependent variables, which were the visual acuity of our users. We measured this using a Landolt-C acuity chart. It's a very common type of visual acuity chart. Instead of having a bunch of different letters, it's all the letter C. It's just rotated in 90-degree increments. So our users just have to tell us which side of the C has the opening. So they'll read it as up, down, left, or right instead of A, B, C, or D. We're also looking into visual fatigue. To measure this, we use a survey called the Convergence Insufficiency Symptom Survey. We give them this after each of our conditions to get a rough estimate of how their eyes are feeling. And this is a pretty commonly used survey for these types of things as well. Our third measure is a usability score. So we use the user experience questionnaire short version after each of our conditions to get an idea of how easy it is to read text on these user interfaces under these various conditions. So our study environment looked like this. Our participants came in, they were seated in an isolation booth at a desk, and then they would be asked to put on the HMD, which in this case was an Oculus Rift S. From there they would read paragraphs that were floating out in front of them for 1 minute to themselves. There's 4 paragraphs, so they go ahead and read those in their head to get an idea on how easy it is to read under these lighting conditions. After that, those paragraphs disappear and are replaced with an acuity chart that we discussed earlier. From there, our participants read as far down that chart as they possibly can, all the way down to the bottom if they can. They take off the HMD after that. They do those 2 questionnaires we mentioned, and we repeat for every condition. So our conditions looked somewhat like this. On the top row, we have our bright virtual environment, and on the bottom row, we have our dimly lit virtual environment, and then we have the paragraphs on our left side of the screen, our acuity chart on the right. The important thing to notice here is that the colors are the same between light mode and dark mode changes. So if we look at the top row at our bright virtual environment, we're using white pixels and black pixels, regardless of which mode is being used. However, when we change the environment to be the dimly lit virtual environment, the contrast level is reduced. Instead of white pixels, they go to a gray color. So we have gray and black pixels. And again, those are the same colors for both light mode and dark mode. So here's our first page of results. These are all our visual acuity results. Here we see that we had on the left side the number of errors made by participants broken down by condition. So on this chart on the left, higher is worse. We want these scores to be low. So we did see a significant effect of our virtual lighting on the number of errors, and that's to be expected. So if we compare the left side of that first chart to the right side, we see that when we're in the bright conditions, we have lower errors, so they're making less errors. And then when we move over to the right side and we dim the lights, they make more errors. And again, we believe that's due to that decrease in contrast that happens just with the coloration of the user interface. We can then break these down by pairs. So if we look at the bright virtual environment on the far left with no perimeter lighting, we see that light mode, our users in light mode made less mistakes than they did in dark mode. And this was a significant difference. When we turn the perimeter lighting on and we go over a column, we see that we lose that significant difference. And then as we continue over without perimeter lighting in a dim virtual environment, we see that users actually made less mistakes with the dark mode interface than they did with the light mode, and this was a significant difference. And then again, we lose that when we turn the perimeter lighting back on. So it's interesting that we're seeing these opposite effects depending on the virtual lighting in the room. On the far right side of the slide, we also have a measure that is the maximum row number achieved by our participants without making any mistakes. So on this chart, higher is better. You want them to read all 7 rows without making any mistakes if they can. So we actually see similar results. We did have that significant main effect of the lighting so that people were able to read further down on the chart in the bright conditions than they are in the dim conditions. We did, however, lose our significant result under the brightly lit environment for no perimeter lighting, and we only see that significant difference in the dimly lit environment between the light mode and dark mode interfaces without perimeter lighting turned on. We also have these measures of visual fatigue, and these were more straightforward. What we found is that color mode does have a significant effect on visual fatigue scores. So when we look at this chart, you want these scores to be less. Less means less eye strain, whereas more means more eye strain. So when we compare our light mode and dark mode columns here, we see that across the board, dark mode does tend to have lower visual fatigue scores. And then there were significant differences for both conditions in which the perimeter lighting was turned off. So to summarize those results, for dark mode or negative contrast user interfaces, we found that our users had better visual acuity in dim virtual environments. They actually had reduced acuity in bright virtual environments, and in general, they had reduced visual fatigue overall. On the other hand, with light mode or positive contrast user interfaces, our users experienced reduced visual acuity in dimly lit virtual environments. They had better visual acuity in bright virtual environments, and they had increased visual fatigue overall. So from this, we have some recommendations for just work in VR in general and user interfaces. And they are to go ahead and use that dark mode if you're using dimly lit virtual environments. You go ahead and switch it to light mode if you're using primarily bright virtual environments. And then if visual fatigue is a concern, or if users are complaining of visual fatigue, switching to dark mode may be a really easy fix. So thank you guys so much for your attention, and I will be around in the chat here to answer any questions that you may have. Thank you.